So thank you for being here. So my name is Sébastien Crozet, and I will be talking about the Rapier physics engine. But first, let's start with a few questions. How would you try to train a robot to evolve in a terrain like Mars? Or how would you train a robot to operate in, I don't know, a nuclear plant where you cannot even access this domain, or even the robot itself could cost millions of dollars? Or how can you train a robot that you don't even have? So that's where a physics engine like Rapier can come into play, where instead of collecting data from real-life robots or real-life videos, you would collect data from a virtual simulation of your scene. So that way, the cost to get this robot is basically free, and the cost to run your simulation is extremely low, both in times, because it can run even faster than real time if it needs to. So in this talk, I won't be talking about how you would ingest your simulation data in an AI model, but more like what kind of features you might be interested in using for robotics, for learning. And I have two parts. So the first part is really about Rapier itself, and the second part would be about very large-scale simulation. So if you wanted to learn or to run your model on a very, very large domain, how you would operate with a physics engine. So Rapier is a physics engine. It's written with the Rust programming language, and it's in the class of rigid body physics engine. So it simulates rigid objects without any kind of deformation, which would be different kind of physics engine, which are also developed with, but it's named Sparkle, so it's a different one. So as far as Rapier is concerned, it can do rigid body physics. Right now, it's being used into at least 3 significant frame modes. So Fireworks is a game engine in Rust. Bevy is also a very popular game engine in Rust. And Crozet is a platform in JavaScript, which lets you write collaborative application very easily without worrying about network code. So across, one of the very interesting features of Rapier is cross-platform determinism, which means that if you enable that feature, you will lose a little bit of performances, but in return, you will make it so the physics engine runs exactly the same way on every single platform. So it will run the same way on macOS, on Windows, with an AMD processor, with an M2 processors, or even on the web with WebAssembly. That way, if you start your simulation, be it for learning or just for games, you are guaranteed to get the exact same result on every platform, which might be actually extremely important for networked application, or just for learning on different kind of devices, if you want to guarantee to get the same result in the end, given the same kind of inputs. So the Rapier architecture is quite typical for rigid body physics engine. It would start with a collision detection step, which is split into 2 subparts, so broad phase and narrow phase. The broad phase, which here is the hierarchical SAP sweep and prune algorithm, is responsible for finding pairs of collisions which might happen. So it doesn't tell you exactly how things are colliding, where things are touching, but it will tell you, okay, these 2 objects are likely to be in contact. The next step would be the narrow phase, which is the JGK plus EPA algorithm, which will compute actual contact points and penetration distances between your objects. And then you have force calculation, and that one is actually a bit new compared to last year, because it's using a new solver called TGS Soft. So TGS is temporal ghost saddle, and we will discuss a bit more about that in the next slide. After that, we have integration, so integrate forces and velocities to get new velocities and positions, and you might optionally loop to get continuous collision detection, which is to handle very fast-moving objects. And finally, we have a verbalized collision detection step to make sure that if you, as a user, start querying your physics engine for different states, like if you want to know, does my robotic arm touch this object, or what's the distance between my robotic arm and that object, you can have an accurate response based on the new positions of your objects after the integration step. So that's like the physics pipeline, the main thing you would use to advance your simulation through time. And you have also a query pipeline, which will allow you to run a static query, geometric query on your scene, which includes like raycasting, shapecasting, some very, very standard operation you might do to make your virtual robot aware of its surrounding. And finally, and these ones are probably less interesting for robotics, you can have a character controller and vehicle controller, but these ones are very like kind of fake behavior, like the kind of things you do in games, but which are not based on any actual mechanical or realistic behavior. So you can probably ignore these two. So I mentioned this TGS soft constraints resolution. So what this is that for a very long time, the main constraint solver in physics, rigid body physics engine, was what we call PGS, which is projected Gauss-Seidel, and it's responsible for computing new velocities based on a set of forces. So TGS soft is a new method, which is very, very strongly inspired by this paper named Small Steps in Physics Simulation from NVIDIA, which was about improving NVIDIA XPBD physics solver to make it much more stable, especially in a situation of large mass ratios. Like if you have, for example, a robotic arm which is trying to lift a very, very heavy object, you have this interesting situation where your object is much heavier than the hand of your robot. And this is actually extremely difficult to simulate for a physics engine because from a numerical point of view, it creates a lot of instabilities. So this is what this small steps system aims to solve, and the way it works is, that you have your simulation step, so the amount of time you want to advance your simulation, you will cut this step into multiple sub-steps. So we will cut this into multiple smaller slices of time, and you will solve each slice of time iteratively. So the main difference here is that instead of running n iterations for your projected Gauss-Seidel solver, you will just run a single iteration, but you will have one iteration for each of these sub-steps here, which is n steps. So TGS soft is kind of the same thing, but replacing everything that's position-based, because XPBD is position-based. It's replacing this by a velocity-based formulation. So this piece of code is not, it's not complete. Like it also has some logic to update your constraints based on virtual movements, but it gives you an idea of how similar things can be, and that you really don't have to operate at the position level to get the same kind of benefits. So if I just show a very, very quick demo to show that even a simple simulation case can be very difficult to simulate, you can see here this thing. So it's basically a bunch of capsules here, and each link is attached by a revolute joint, so just a single rotation. And at the end, you have these very, very big spheres. It could be a small sphere, but here it's a big one, just to show that this big sphere is significantly heavier than all the rest. So if you look at what the most common physics solver, projected Gauss-Seidel solver does with that, you will see that it starts falling and then it completely breaks down. So this is caused by the numerical instabilities. And if instead of using 4 iterations, I switch to 40, you can see that it's actually not better. And now, let's say I switch back to 4 iterations here, and I go to the TGS soft, so the new solver. You will see that things changed a bit here. So instead of having 4 PGS iterations, I just have 1, but instead of having one substep, I have 4. And now you can see that even with just 4 iterations, things are much more stable. We do have a little bit of stretching when the ball is more like here. We have some stretching, but it doesn't break down like before. And if I go and use 40 iterations, you can see that things are very, very much stiffer and very closer to reality. So all that to say that, especially for robotics application, this new solver is very interesting because you generally have very difficult constraints to solve, and also manipulation can involve some arbitrarily large mass ratios between objects. So, and just to show that this one, like this example, is just involving joints, but the large mass ratio problem is also true for just collisions. So if I switch back to the old solver, you can see in this scene, like the one cube on top is much heavier than every other cube. You can see that here it just does some very weird bouncing and pushing. But if I switch back to the new solver, it's significantly more stable. Okay, so TGS Soft is not something specific to Rapier. It's becoming increasingly used in modern physics engine. So the one I'm aware of is BoxStudy. So the latest version of BoxStudy, which was released a few months ago, does also use the same kind of solver. So 2 other features you might be interested in if you are writing a robotic application would be a URDF file loader for Rapier. So this is the Rapier 3D-URDF crate. So you give it a URDF file, and then it will parse the file, create joints based on what is in the URDF file, and also create meshes based on the shapes you have. Right now, it only supports STL, the STL format for the mesh files, but we are working on extending this to a lot of more mesh formats. And the last, so these two here are actually 2 URDF models which were loaded with Rapier 3D URDF. And one last feature you will be probably interested in is inverse kinematics. So in the video here, you can see that I'm using a gizmo to move the objects with the mouse, and you can see that like the joints are changing their position automatically based on the prescribed position by the gizmo. So this is what inverse kinematic does, and it works with every joint supported by Rapier, which is any kind of combination of degrees of freedom you might want. And one thing you might need to, one last feature you might be interested in is that Rapier has 2 modeling of joints. You can model joints using forces, which is something robotics doesn't really like in general because you can have the kind of stretching we saw earlier. But you can also simulate joints with what we call reduced coordinate modeling, which means that your joint positional constraint is directly part of your equations of motion. And this is the case here, which means no matter how you move your object, you will never have any violation of the joint constraint. So it will always match what your actual robot is able to do with its arm. You don't have some weird drift between different links. It does come with an extra computation times, and very sharp changes in velocities can be unstable, but in general, in real life, you don't really have this. Okay. So that was for Rapier itself. Now let's see how we could extend this to extremely large scenes, like with 1 million objects. So this part of the talk is kind of the continuation from last year. So if you saw my talk from last year, you will see a lot of overlap, but also a few updates for things I've changed in the design of the distributed system. So first, what do we want to simulate with distributed physics? We could think of two kinds of scenarios. You could think of this huge tower of cubes with a lot of cubes. This is not what we are interested in, because this is not what we will typically want to simulate for a game, for a metaverse, for any kind of navigation system. You are really more interested in this kind of situation where you have like a lot of buildings in a city, for example, a lot of, I don't know, a lot of humans moving around, but everything is kind of scattered through space, not like stacked into a single location. And these two are actually very, very different from a mathematical perspective, because on the second one, you have very strong interdependency between each object because of the way forces work, whereas on this one, we don't have that much dependency, so it's much easier to solve efficiently in a distributed system. So the general idea is kind of what you would intuitively do for any kind of spatially based work distribution. You would split your domain, your spatial domain, 2D or 3D, into subdomains. And the easiest approach would be to split your domain into a grid like this, and you say, okay, I have one instance of my physics simulation running on each of this region of my domain. Now, of course, if you have one instance of the physics engine simulating different independent regions, you cannot have any kind of interactions between objects crossing boundaries. And this is where things get tricky in the distributed simulation. Like if one object from this region starts moving to the one of the right, what happens? How do I say, okay, I need to stop simulating my object, send this to another instance of the physics engine? This kind of problem. So we have two key concepts here. The first one is the concept of island, which is not specific to distributed systems, but it's something very common in physics engine. So what you do is you have a bunch of objects in a stack, and you will isolate each individual stacks. Why you want to isolate this? It's because any force applied between two objects on the same stacks has a mathematical dependency on every forces acting on every object on the rest of the stack. So if you want your simulation to be correct from a numerical perspective, you really want to be sure that all the constraints here are known for your constraint solver. You cannot just solve these two separately and then these three separately and hope that it will work. It's really a global optimization problem you have to solve. So the concept of island is basically how much objects need to be part of the same mathematical problem to create a correct result. So this is important because what this means is that a single Rapier or any physics engine instance has to simulate a complete island independently from how it's scattered in space. And you will see a schematic just after. The second concept here is that we have our grid, and we want to have some kind of spatial ordering of each region on this grid. This spatial ordering will help decide where objects need to be simulated. So here I'm giving a spatial index to each of my region in space, and everything is sorted based on the lexicographical ordering. So here, everything that's green is considered to be larger based on this lexicographical ordering than the 00 cell here, and everything that's orange is considered to be smaller. So if we go back to islands, if we look at this system, we see that we have a bunch of islands which are crossing boundaries of multiple different regions. So like I said, we cannot have different objects from the same island being simulated by different instances of the physics engine. So we need to make sure that everything in red here is simulated by the same instance of Rapier. So what we do is that we look at the bounding box of the complete island, and we will say that whichever region contains the maximum point of this bounding box is responsible for simulating the complete island. So this one, the red one, for example, will be simulated by the 1-1 region here, but not by any of these three other regions. And the blue one will be simulated by 1-0, and the orange one will be simulated by -1, -1. And this is despite the fact that objects are crossing boundaries. Now, what happens is things start to move. Then we have three kinds of situations. The first situation is if it's moving and crossing the boundary toward a larger domain, we will see that here the max point of our cube is entering 1-1, so we are simulating, like the region 0-0 will give ownership of the object to the region 1-1 and stop simulating my object so that 1-1 can take over the simulation. And here I'm just showing a single cube, but in reality it could be a complete island. So this could be the bounding box of a complete island. So same thing if I move backward. The only difference here is that here it's still crossing the boundary, but it will be simulated by 1-1 because the max point is in 1-1. And here the complete box has to be inside of -1-0 because it's a smaller region. And the last situation is actually much more complicated, is that if we have this case where my object is moving but remaining inside the same region, so inside of 0-0, but it starts interacting with one object which is simulated by 1-1. In this case, we have a merge of islands, so these two ones are supposed to be simulated by the same physics instance, but we need to detect this situation because 0-0 does not know about this black box. So it doesn't know that it's supposed to interact, so it's supposed to start being simulated in the same set as the black one. So we have a concept of watch set, which means that any of these black objects or black islands which are crossing the boundary between a green and gray region has to be inserted in a watch set, and that watch set has to be loaded by the region, the gray region. That way, the gray region is always aware of its surrounding and is always aware that if one of its objects starts crossing one of these watched black objects, it has to give away ownership of what it's simulating so that the complete island can be simulated in one of the green regions. So in terms of infrastructure, and this is where things are actually quite different from last year, and in a way much more simpler, we have two kinds of nodes in our cluster. We have a master partitioner node, which is the orange one here, and we have a bunch of runner nodes, which are the blue ones. Communication is handled by Zeno at any stage of this system, except for communicating with the client, which will communicate using just a simple API with the master node. So this master node is responsible for a few things. The first one is responsible for deciding where each object has to be simulated. So it will test this maximum bounded box points to dispatch the object to the right region. And it will also be responsible for assigning a new region to one of these runners based on how much load is already on one of these runners. The partitioner is also responsible for time synchronization between runners, because we don't want one runner to simulate 10 years of simulation, whereas another runner, being slower, will simulate just a few seconds. So the way it works is that this master node will have a partitioner which will send a step message to all the runner nodes, and the runner nodes have a local instance of this partitioner to send step messages to all of the Rapier instances. And when the Rapier instances are done simulating, they will send back a step-ended message to the local partitioner, and the local partitioner will follow this step-ended message to the master partitioner. And when the master partitioner has received all the step-ended message, that's when it knows that it can move forward to the next step. Now, in practice, doing this 60 times per second would be way too slow. So we instead run multiple steps as a result of a single step query, but we have to account for the fact that we get some movement due to that many steps, so we need to adjust our watch sets accordingly. So this is done, so it's a bit more involved, but this is done by, instead of taking the static position of one object for the watch set, we can actually use a predictive position system which will take every possible intermediate position configuration for my island that needs to be watched by one other region. And finally, if the client needs to get some information about the objects, instead of going through the API, it will directly query Zeno, which has a very, very nice feature, which is called queryables, which you can use to send a query, broadcast a query that then, based on like the path of the query, a given runner will know that it is responsible for returning the desired information, and in particular, it can be used to return positions of objects. And the reason queryable are very, very nice is because you can have some custom code, which, as a response to a query from the client, you can filter some objects out. In particular, if some objects stopped moving for a while, we can just ignore sending these positions back to the client to save quite a lot of bandwidth. Because in reality, like in actual physics simulation, 90% of your objects will not move until something starts interacting with them. So there is really no point in like sending position information or velocity information or whatever the client needs again and again if in reality it didn't change. So in conclusion, you will find a few links. The first one, distributed physics prototype, is like for the distributed physics part I mentioned. And again, I use Rapier because that's the physics engine I make, but it could really work with any kind of physics engine which has the same kind of concept. Like the island concept, I think every single physics engine out there do the same. So you could reuse the internal island information as part of your dispatch system in the distributed system. Rapier, the Rapier repository is the main physics engine repository. That's where you will find the source code for the TGS solver, and also where you will find the source code for all the examples, including the one I've shown. And then a special mention for a new project I've been working on for the past few months, and I made a presentation yesterday on that, but one thing that's very interesting is that today this distributed system is very nice because you can simulate a lot of objects, but what if you want to go one order of magnitude further, or even if you are not in the distributed system settings, what if you really need an absurdly large amount of data for your training system? Then you need something that runs very, very fast. And also, one more thing is that today most training system would run on the GPU, so it would be very, very nice if we could train our robots and the training data system would also run on the GPU so that everything remains extremely efficient and without any intercommunication with the CPU. So all of that is leading to the question of how can we leverage GPU for physics simulation, but not only physics simulation, how we can leverage the GPU for everything, like any kind of community, any kind of scientific domain, so that we can start collaborating around the same code bases for GPU compute. And we can mix AI, physics, all on the GPU. And this is what this new project is about, which is named WGMath. And this is a link of the WGMath project. Okay, so thank you very much for your attention. And if you have any question, I'm here.
Yeah, thanks, Sébastien.